In this video, we're going to introduce the incidence algebra of a poset. Eventually, the long-term goal is going to be present a vast generalization of the principle of inclusion-exclusion. And that vast generalization involves the incidence algebra. So given a partially ordered set P and two elements little p, little q in the poset P, we define the interval square bracket PQ to be the set of all elements that are between P and Q. The square bracket notation is the one we get from calculus. When in calculus you talk about A, B being the set of points that are between A and B. So it's the same idea. We still use the same terminology. Similarly, if you see open parenthesis, that's an open interval, so that would be where you allow strict inequality. We're going to let int of P be the set of intervals. And the incidence algebra is going to be the set of all functions from intervals of P to the complex numbers. And we're going to define a multiplication operation on the incidence algebra. So that means f times g is going to be another function from the intervals to C. How would you define that? Well, you have to define what it does on an ordered pair PQ. Here, of course, I should make it clear from context. Whenever I'm writing PQ, we're looking at elements P and Q in our poset such that P is less than or equal to Q, because that's the only case when you actually have an interval. And so instead of writing square brackets PQ to represent the interval, we're just going to refer to it as an ordered pair like this. So it's an abusive notation, but it's worth pointing out that is what's going on. Whenever you're working with an incidence algebra with two ordered pairs, it should be clear from context this is referring to a function on intervals. And how do we define it? We define f times g applied to the interval PQ to be the summation over all r in the interval, f of PR times g of RQ. And it's a theorem we're going to prove that the incidence algebra is in fact a ring. So here I'm assuming you know the definition of a ring. And in fact, we're actually not going to show all the properties. We're just going to show that this convolution product is associative and that it distributes over the natural notion of addition, which would be pointwise addition, f plus g. So I'll include it. F plus g of PQ naturally should be the sum, f of PQ plus g of PQ. And to make this stuff a little less abstract, I'm going to focus on this other subalgebra, the invariant subalgebra. This is going to be the set of those functions where f of PQ is equal to f of P prime Q prime whenever you have two isomorphic intervals. And so I'll mention this in a little bit before I do this proof. So as a first example, let P be the poset of all natural numbers under the standard partial order. Then given I and j, natural numbers with I less than j, it's not too hard to see that this interval is isomorphic to the interval from 0 to j minus I. Literally by just taking an arbitrary element and subtracting I from it. Also known as the fact that both these, their Hasse diagrams, is a vertical chain of length j minus I. Then a function is in this invariant subalgebra if and only if f of ij is equal to f of 0 j minus I. In particular, that means that you're really looking at a sequence. So define a sub j minus I, or a sub n, in general, to be f of 0n. And then you see that really these functions correspond to sequences. What does this convolution correspond to in this case? Well, f star g of ij is f of ik times g of kj, as k ranges from I to j. But you can replace this first sequence with a sub k minus I. You can replace the second thing with another sequence corresponding to the value of g, because we're assuming g is also in this subalgebra. Now if you reindex the summation by replacing k with k minus I, and set n equal to j minus I, this summation becomes the sum as k goes from 0 to n, a sub k, b of n minus k, And now this convolution looks familiar. This is the convolution of ordinary generating functions. And so this subalgebra is isomorphic to the algebra of generating functions. So the point there is that you can view this as some sort of generalization of ordinary generating functions to arbitrary posets. We'll see this with the next example too. As another example, let P be the set of all finite subsets of N under inclusion. It's not too hard, given two subsets S contained in T, that this interval is isomorphic to the interval from the empty set to T take away S. How does the bijection go? You send R to R take away S. And since T take away S is a finite set, there's also a bijection here that depends on fixing a bijection from T take away S to this set. So I'll do that bijection in a bit. How does it work? So if you fix a bijection from T take away S to the positive integers of the subset of integers 1 through size of T minus S, you know such a bijection exists because that's the cardinality of this set. Then given a subset X of T take away S, define f of X to be f of little x for all the elements of X. This in fact is a subset here. And you can go backwards by using the inverse of this bijection, and these two intervals are isomorphic. In particular, for a function in this incidence algebra that's invariant under isomorphism, f of st is actually constant. It's equal to f of the empty set and then this set. So it's completely determined by these values. In particular, it's completely determined, this invariant is completely determined by its values on the empty set and the set of positive integers 1 through n. So will a n be that sequence? Given another function g, so let's point out we're looking at f and g are in this invariant incidence algebra of this particular infinite poset. They're determined by these sequences. Then if you run through the calculations for convolution and you take advantage of this stuff, you'll eventually see that f star g applied to st ends up being this binomial convolution because of this special case. So in particular, you're going to get the convolution for exponential generating functions. And so you see you're sort of generalizing the two different convolutions for generating functions. A third example, which we won't discuss much further than this, is that you can look at natural numbers under division. Then this incidence algebra is actually going to correspond to something in number theory called the ring of Dirichlet series, which has its own convolution. And so it's sort of generalizing things from three different areas of mathematics, all simultaneously. Although for most theorems, we're actually going to assume P is a finite poset. But the point is there's somehow this relationship. Unfortunately, the relationship's related to this. In general, for the arbitrary incidence algebra, you don't get such a nice feature. Although it turns out there are plenty of counting problems where you're looking at incidence algebra in general. So now let's prove that the incidence algebra, this multiplication, is associative. So how do you do that? You take three functions in the incidence algebra, and you want to show f star g star h is equal to f star g star h. And how do you do that? Well, they're functions, so you have to take an arbitrary input and show they're equal. They both have the same domain at least, so that part's clear, and the same codomain, so that's all you need to check. Again, that means you need to take a p less than or equal to q in the poset, and you're looking at what the functions do to the interval pq. So what does it do? Well, by definition of convolution, you're summing over all s in the interval pq. First function applied to p comma s, second function applied to s comma q. But this first function's also a convolution, So by definition, you calculate it by summing over all r in the interval ps, f applied to pr times g applied to rs. However, multiplication is distributive, so I can distribute this product to the inside and have one summation, double sum over all s in pq, and then over all r in ps. F of PR, G of RS, H of SQ. Please note the RR and the SS. And I can combine this summation into a single sum by saying I'm summing over all ordered pairs RS, where P is less than or equal to R is less than or equal to S is less than or equal to Q. And theoretically, you could have defined this, although we're not going to be the triple product. So this is worthwhile because it tells you what happens. You get this summation. Now, on the other hand, what happens if you compute this function? Well, by definition of convolution, I sum over all r in pq, fp applied to pr, and then the second function applied to rq. Again, by convolution, this is computed by summing over all s in the interval rq, g applied to rs, h applied to sq. Again, the distributive law holds, and I can distribute the fpr through like I did before, and I have fpr, grs, hsq. And then again, this summation, it's over all r and then over all s. I see that I can combine it into summation over ordered pairs rs. And now if you look at the previous slide, you see I have the exact same summation that I did before, and therefore our multiplication is in fact associative. And since P and Q are arbitrary comparable elements in P, with P less than or equal to Q, these two functions are in fact the same. Another property of rings you need to show is the distributive law, that multiplication distributes over addition. Technically, you need to show both directions, particularly since in this case, convolution is not commutative in general. So technically, there should be a second part of this proof that I'm going to skip because it's similar to this part. Just by writing everything, moving everything to the other side. So to show inequality like this, so what does it mean to be distributive? It means f times g plus h is equal to f times g plus f times h. These are functions, so how do you prove equality of functions? Well, you show that when you apply this function to every point in the domain, you get the same result. So let's evaluate at pq, where p is less than or equal to q. By definition of convolution, you're summing over all r in the interval pq, f applied to pr, times g plus h applied to rq. Our definition of addition is pointwise, so f plus h applied to rq is, g plus h applied to rq is g of rq plus h of rq. Multiplication distributes over addition, and so I get fpr grq, fpr hrq. Addition is commutative, so in particular I can sum over all r of these two sums, or I could separate this summation into two separate summations. So I group all these first terms together, summing over all r, fpr grq, plus I group all these second terms together, I'm summing over all r, fpr hrq. But this is just the definition of f convolved with g applied to pq, and this is just the definition of f convolved with h applied to pq. Since addition is pointwise, this summation is equal to this one. And so there's one distributive property. The other distributive property follows similarly. I guess the cheap way is you move everything, all the f's over to the other side, and you rewrite the order of these elements. So this is qr, rp, and this would be qp. It can be done. So it is a distributive ring. Now we look at examples of functions in the incidence algebra for any poset. So let P be any poset. We're going to define a particular function called u. U of PQ is going to be 1 when P is equal to Q and 0 otherwise. So for instance, let's let this be our poset. Look at the point x and y. U of x, y is 0 because x and y aren't equal. And it's worth pointing out, if you run through the convolution, f star convolve with u is equal to f is equal to u convolve with f. I can at least do the first one, I guess. If I apply this to PQ, we know by definition of convolution, we're going to sum over all r in the interval PQ. F applied to PR, that should be u here. U applied to RQ. Well, when u of RQ is 0 in all cases except when r is equal to q. So the only term in the summation that survives is when r is equal to q. In all other cases it's 0. And in that one case, that second value is 1. And the first thing is just f of PQ. And by golly, that's just f of PQ. And so you see, when you convolve f with u on the right, you get f back. So in modern algebra terminology, this is a multiplicative identity in the incidence algebra. So it plays an important role when you're talking about inverses. When you have a multiplicative identity, you can start talking about multiplicative inverses with respect to convolution. And as we saw with inclusion-exclusion principle, or with generating functions, it's sometimes important to know about the existence of multiplicative inverses. One of the most important invariants or functions that are in the incidence algebra, so again, arbitrary poset P, we're going to find zeta based on this rule. Given P less than or equal to Q in your poset, zeta of PQ is always defined to be 1. And so it's 1 everywhere. And so if you extend P to a complete total order, and then you write down the defining matrix, you actually get a diagonal matrix. Not diagonal, upper triangular. The interesting thing you could ask is, what happens when you convolve zeta with itself k times? Well, by definition of convolution, you should be summing over a sequence of k things in this interval. In each case, you're supposed to apply zeta of the appropriate interval. So technically, I should be careful here and actually point out that this summation, you should see zeta p1, p2 times zeta p2, p3, all the way up to zeta of pk minus 1, pk. But each of these numbers is 1, so this product is just 1. So in particular, this is counting the number of k multichains in your interval. Not in the entire poset, just the interval you're interested in. Now, what if you're interested in counting k chains? Well, all you need is eta, which is zeta minus u. So it's 1 when p is strictly less than q and 0 otherwise. Then when you do this convolution, if at any point in time pi is equal to pi plus 1, that factor is 0, and so that term vanishes. And so then you only get cases where each of these is 1, which means that you actually have strict inequality. So eta to the k of pq is the number of k chains. Going back to our examples, let P be the power set of X, so it's the subsets of X under inclusion. Let S be a subset of T, be a subset of X. Then what's A to K of ST counting? It's counting chains of length K, where S1 is equal to S and SK is equal to T. Let's look at an example. X is the set of integers 1 through 9, K is equal to 4, S is the singleton 1, and T is everything except 7. Then since k equals 4, we're just looking at, all you need to do is specify two sets, one containing one, containing the other, so that we got a chain of length 4. Well, how many ways can we do that? Well, if you let xi be the set difference, you see what you need. So you need to specify the elements in this set that aren't in that in some number of ways, the elements of this set that aren't in that in so many ways, and so on and so forth. And so it's not hard to see that what you're looking at is this multinomial coefficient. So suppose we sum chains based on the sizes of these set differences. the sizes of a set difference is going to give you an integer composition of size t minus s. Given that integer composition, this multinomial coefficient is choosing the elements here that are new. So delete what's old. So for instance, choosing 3, 5. The next coordinate here is telling you how many ways to choose the elements in the set difference, so the things that are new, 4, 5, 6, and so on and so forth. And so it's possible to do a bijective proof showing that eta to the k of st actually has this closed formula. It's actually quite horrible, but it does tell you how to solve, at least in this example, what these functions look like. Admittedly, if you go back to exponential generating functions, you'll see this looks similar to the binomial convolution we had there. The only difference here I should specify is that each of these is an actual integer composition. They all have to be positive because you can't have equality in this chain at all. As another example, let P be the set of divisors of n. What is eta to the k of 1, n count? Well, you're counting chains in this poset, which means each entry has to divide the next because that's the partial order you're working with. And so in particular, that means this entry should be written as n1 times an integer. This entry is going to be n1 times n2 times another integer. And so then you can go backwards and you now have this sequence of integers. And you see when you multiply them all together, that has to give you n. More importantly, because these are strict inequalities, these quotients, these new integers, all have to be bigger than 1. And so what is this counting? It's counting the number of ways to factor an integer as a product of k minus 1 positive integers that are all strictly bigger than 1. So as an example, let's look at eta to the 4th of 1 in 60. Well, then you're looking at ordered factorizations of 60 as a product of 3 numbers. And so one such factorization, ignoring order, is 2 times 2 times 15, or 2 times 3 times 10, or 2 times 5 times 6, or 3 times 4 times 5. But remember, we're talking about ordered factorization, so order matters. There's 3 ways to permute this one because these two numbers are identical, and 6 ways each for these 3. And so you get that this answer is actually 21. And so the whole point here is if you're working with an arbitrary incidence algebra, you can define these invariants, and then for particular posets, you're actually studying a specific counting problem. But the point is that each of these counting problems has this common generalization. So any theorem you prove about this invariant immediately implies information in these special cases.